I mean, the wheels on the table. Yeah.
Yes. That was not due.
I think we're ready to go. Is it? I guess maybe my watch is a minute slow. It's 11. All right. Okay, I'll start. Okay, welcome to the. Yeah. Right. Okay. Yeah. So some logistics. So okay, we're continuing now with the Pure course. My name is Gabe Conant. I'm visiting here at Fields. And yeah, I'm just doing two sections, and that will finish the course, or two things. So this week and next week. Next week we're starting at 9 in the morning because there's a conference next week. So it'll be the last one will be 9 in the morning, but on the same day on Tuesday. Right. So the title on the website I think was Stability and Combinatorics. I'll obviously be clarifying what exactly I'm doing there. And since I'm just doing these two courses or these two sections, I mean, it might feel a little less like a course and more like a tutorial in terms of how many definitions and proofs and stuff I have, but I hopefully it'll still be relatively thorough. It's going to connect more directly to what Anand was talking about. In fact, right at the end, the last thing he did in local stability, rather than connecting so much to Atai's course. And you might not see that connection until next week when we actually do the model theory proof. Most of today will be setting up the combinatorics framework and saying a little bit of the model theoretic framework too. So I'll just get started. So I've kind of divided up the two, what do we call it? Course lectures, class times. I've divided up into kind of three parts. So the first part is going to be kind of overview, stable, graph regularity. Also, I think that for the people who are coming to more than just these courses, if you're coming to the Fields, our seminars yesterday and Wednesday, and also the combinatorics workshop next week, this will all be very much thematically related. So I think it'll fit nicely. Okay, so I'm going to start by stating a result called Zemretti's regularity lemma for graphs. Before I do that, I will set a little bit of notation. So I'm going to start by talking now about just graphs. So given a finite graph, so by a graph, I mean a vertex set and then an edge set of pairs. You can think of it as symmetric or reflexive relation. Let's see, and given two subsets of the vertex set, X and Y, I'm going to define this notation for like the edge density of the graph on this pair. So I'm going to use delta XY. It's just the kind of the number of, I guess, ordered edges. If you like, we won't have to worry so much about this. So if I think about the edge set as being a set of pairs, I'm just taking the size of that divided by the total number of ordered pairs. Okay, so now I'm going to state Zemretti's regularity lemma. It's very big. See if I can fit it here. So this is like kind of like an approximate structure theorem for large finite graphs, which is more meaningful when the graph has a lot of edges, so it's somewhat dense. And it says the following. well, there's many different ways of formulating it. I'm going to pick one. So for every epsilon greater than 0, there exists some integer n which depends only on epsilon, such that if I have some finite graph v comma e, and I have kind of a sufficient number of vertices, so I think this is accurate, but then the size of the vertex set is at least, say, 1 over epsilon, then I can partition this vertex set. So there exists a partition V. So it's going to be V0 union V1 union dot 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 union Vn, little n. And okay, this little n is going to be at least the number of vertices and at most this bound, depending only on epsilon. Yeah. Yeah, is that okay? Yeah. Okay. Yeah, yeah. So no. Yeah, right. No, little n is not the number of vertices. Maybe, I mean, yeah, sorry. Okay, I could change this to m if that would be better. Yeah, actually, that's a good. There's a good reason to change it to m anyway. Okay, so I changed this to m. So this is the number of pieces, and what happens with this partition? So such that two properties. So part one, make sure everybody can still see it, is that okay? This V0 is going to be, think of it as like an error set, an exceptional set of vertices. So it's small. So the size of V0 is at most epsilon times the size of E. And for all the rest, so for ij at least 1, the rest have exactly the same size. So the size of Vi equals the size of Vj. So it's a very structured partition, small set of exceptional vertices that you ignore, and the rest have the exact same size. And then the second part is the regularity condition, which says that most of the pairs among the V1 up through Vm give you something called an epsilon regular pair. So I'll say what I mean. No, they're supposed to be how I've written it. They're exactly the same size. Yeah. So I will say things. So maybe, you know, let me finish writing the statement and saying some remarks, and then if there are further questions, we can clarify it. Okay, so what does it say? So for at least 1 minus epsilon. Now I'm going to be more careful than combinatorics usually are. Okay, how many possible ways are there to choose a pair? It's m choose 2. So for at least 1 minus epsilon m choose 2 pairs, ij unordered here for this count. This stuff doesn't matter so much because they're all kind of roughly equivalent. And now here I'm looking at pairs ignoring the exceptional set. So with ij greater than or equal to 1. So I'll just stick this one moves. Yes. I'm just going to go right to here if that's okay, and then leave it. So this pair Vi comma Vj is epsilon regular. And what does that mean? So i.e. Yeah, so I mean we're going to be going in the setting of stable graphs, in which case this definition is going to disappear. So if you don't digest it, it's okay. It's better to think of it kind of what is the idea. It's saying that this pair is behaving like kind of like a random graph of a certain density. Like you pick a probability and you put an edge at that probability, and this roughly is going to look like that. But to be precise, it means if I take any subsets x contained in Vi, y contained in Vj that are sufficiently large, so with size of x at least epsilon times the size of Vi, size of y at least epsilon times the size of Vj, if I compare the density, the edge density just on these subsets to the edge density of the whole pair, this is at most epsilon. Yeah, so well, you can count how many possible ways would there be for I to equal j. That's m. And so if I change this to m squared, which is what people would mostly do, then this disappears up to, you know. Yeah, so I mean, in the most cases, I mean, if I equals j, you could just ignore it or think of it as one of your irregular pairs, because that's it. asymptotically m is much smaller than m squared. So those are going to be small anyway. This is sort of an important question because when we move to the stable situation, it will be different. Yeah.
So why do you expect this to be true? I mean, what's the intuition?
The intuition is that I never met Zemmoretti, and I don't think I've ever heard him speak, so I can't do an impression of him, but I like to imagine him as being, I don't know, sort of like a oracle type person or something. And I think the quote is something like, no matter how much chaos you give me, or no matter what you give me, no matter how chaotic, I will always find order in there. I think he says something like that. So I think the intuition is that if you take a mathematical object and you allow yourself some kind of error, you can always kind of look for these two extremes, very structured things, very kind of random or uniform things, and then some interaction in between. And so this is about trying to like isolate those parts, those ingredients of a mathematical object, the very structured part, which is this nice partition, and then the very pseudo-random part, which is there once things are large enough and dense enough. So, but other than that, I don't know. I mean, that's probably a really deep question. What's the intuition for this?
I mean, was there some history leading to this? I mean, people were looking at something similar, or
well, okay, yeah, this isn't really the point of what I want to talk about today, but Zemmoretti this was motivated by additive combinatorics. There was this conjecture that if you have a dense set of integers, then it contains large arithmetic progressions. Roth proved this for 3-term arithmetic progressions using some kind of methods. Zemmoretti proved it first for 4-term arithmetic progressions and then for arbitrary. And to do that, he developed this graph regularity. So you should think of it as a tool for studying things rather than like the end result or the final, yeah. And then to go back to Itai's question, right? So if you're familiar with this, sometimes instead of having this exceptional set V0, you will instead of saying these have exactly the same size, you say that they differ by at most 1. These are equivalent. Okay, so clearly, if I have an equipartition in the other sense, where the vertex sets differ by at most 1, then just remove at most one piece from each one, call that V0. That will be a very small exceptional set. Conversely, if I have it stated like this and I want to get rid of the V0, so Caroline explained this yesterday, well then just take V0 and start distributing them one by one in all the rest of the pairs. At some point you might stop. You might not stop evenly, right? So that's why you might be off by 1, but you can just distribute them and then you can check the regularity property doesn't change by maybe 2 epsilon to 2 epsilon or something like that. So I'll let you think more about that. Okay. Now, oh yeah, so the last thing I want to say, I would like to just put it, can people read here? You're the ones. Okay, so this is the last thing.
It's not there.
Huh? But not here. Okay, I'll put it right here. How's that? So one last thing I want to say is, right, so the quantitative aspects of this situation are going to be both important and not important. Okay, so you might ask, what does n epsilon look like? What is this bound? So the proof, Zemmoretti's proof, it's very bad, and Gowers later showed that this was necessary. So Gowers showed that necessarily in this general statement, n of epsilon has to grow something like an exponential tower of 2's. So like 2 to the 2 to the 2 dot 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 dot. How many? Something that looks like 1 over epsilon to some number. I think it's 3 or 5 or I don't know. But okay, that part's not important. Okay, so I'm going to make some side remarks about quantitative things, but then at some point we have to let go of it. Right. Okay. So that's really all I'm going to say about the general regularity lemma. What I'm going to talk about is stable regularity. There is a proof using ultraproducts and some analytic techniques. So there are a lot of different proofs of this. And there are also a lot of different proofs of Zemmoretti's theorem, which was the main application using various techniques. Okay, so let's talk about stability. So definition, I didn't number everything. I hope that's okay. Right. So fix an integer k greater than or equal to 1. Then a graph, and now this could be an infinite graph, possibly. By infinite, I mean the vertex set could be infinite. Then a graph VE is k stable if the formula EXY, thinking about it as a binary formula, does not have a k order property. So let me write it down. So if there do not exist V1 up through Vk, W1 up through WK in V such that I have an edge. So I'm going to write it like this to say that the pair is an edge. So E, VI, WJ, if and only if I is less than or equal to J. Okay, so a K-stable graph is one where the edge relation omits the K-order property like this. And so then it was kind of a folklore result. I don't have all the names here, but you can, well, I'm going to put up the Malliaras-Shalat theorem in a second so you can look at their paper for references. But it was kind of a folklore result that said that people knew that if you have graphs that are not K-stable, graphs that have these big order properties, those are the ones that are going to witness the necessity of this part here, the need to have some irregular pairs in Semeretti's regularity lemma. So you have to allow some of the pairs to be irregular. So folklore, unstable graph. I'm just going to state this informally. The precise thing isn't so important. So unstable graphs witness the necessity of some irregular pairs in Semeretti's regularity lemma. Okay, so you can't reprove that lemma in general for arbitrary graphs and say that all of your pairs are regular, even if you do this regime where you allow the V0. Okay. And so then what Malliaras and Shalat proved was like the converse of this, that if you do look at graphs that are K-stable, then you can prove a version of the regularity lemma where you get rid of the irregular pairs and do more. So I'm also going to state this theorem kind of informally too, because I'm going to state a more precise version that we will be proving in a second. But I want to first kind of give the theorem as they stated. No, I'm going to move. I'm going to move to bipartite in a second, but okay. Partly to like accurately represent what's in their paper, but also to kind of explain to people that this isn't a huge deal. Yeah. So, but okay. So this is Malliaras-Shalat. From about 2000, so like 10 years ago now. Okay. So yeah, I'm just gonna state it kind of informally and say, and then I'll put a precise statement in the bipartite setting because that's going to be what we will actually be proving. So they proved Semeretti's regularity lemma for K-stable graphs plus more. So there's going to be several things to write here, but the first thing I want to say is what this means is that you fix K and you think of that as being a fixed parameter. And so then now your bounds will depend also on that, not just epsilon. So I want to, so n epsilon becomes something depending on both epsilon and K. So you think of K as being a fixed parameter, you look only at K-stable graphs. And, you know, sort of the main thing to get motivated by this folklore fact is to get no irregular pairs. So with no irregular pairs, but then they also got more. So, and again, there will be a more precise statement in a second. So moreover, they proved that in all of the pairs, so all of the pairs, ignoring the exceptional set, all of the pairs are regular, but moreover, they have the density of the pair is close to 0 or 1. So I'm going to write that down. So for all ij greater than or equal to 1, if I look at the density of the whole pair, vi, vj, it's either less than or equal to epsilon or greater than or equal to 1 minus epsilon. So these regular pairs aren't just like regular graphs with some arbitrary density, but they're like almost complete or almost empty. So we're seeing kind of like more complete structure emerging here in the thing. And then they also proved and this is the part that we'll have to let go of, but it's a very important part of their work. They also proved that in this case, the bound is much, much better. So they proved something like n epsilon k grows, instead of a tower of 2s of height 1 over epsilon, it's roughly 1 over epsilon to some constant that depends only on k. I don't know what it is off the top of my head. Well, I kind of do, but I don't want to get into it. Okay. All right. So for stable graphs, we have a strong form of the regularity lemma where there are no irregular pairs. The density of the pairs is close to 0 or 1, and you get better bounds. Okay, any questions? Yeah.
So what do you mean about the density? That's the statement with for all x and y still appeals or not?
Yeah, so it is the statement of the regularity lemma. So it's that statement.
Oh, and
Plus,
you know that. Okay.
Plus no irregular pairs, plus control on the density, plus polynomial bounds. Yeah.
But it's worth saying that knowing the density is close to 0 or 1 implies regularity.
Yeah, so this will come up in a second. So we're going to now start cleaning up, consolidating exactly what do we want to prove, and then I'll be explaining exactly how it connects.
So you mentioned before that the example of regularity is random graphs, but it also includes compute graph and edge graph.
Well, you could think, I mean, if your probability of an edge being 1, you know, then the random graph doesn't look very random. Yeah, so that's why the word you have to be careful with the word. Some people say uniform, quasi-random, pseudo-random. Anyway, so it has to be a little bit like, yeah. Okay, so what are the goals then of these two lectures? So the goals are going to be a model theoretic proof of this, or what I really mean is a slightly different statement that is related. So model theoretic proof. And what this is going to mean, we're going to be using model theoretic methods involving ultra products, so we will not get quantitative information. So I just want to say this now, and then we'll just forget about it. So without quantitative info on the bound, the model theoretic proof will only give the existence of the bound. So now let's just forget about polynomials and exponentials and towers and stuff. The proof strategy using the model theoretic stuff, so it's going to touch on what Professor Pillay was doing in his course, and this strategy is essentially following a paper that is also with Maliaris. So Maliaris, Pillay, they wrote a paper in 2015 giving this basically this model theoretic proof. Although we're going to make some changes. So there will be some combinatorial improvements. Which are were kind of like known in the while, or known for a while, but mostly due to Terry, but now are sort of part of this work, this recent work of Terry and Wolf, which is really about hypergraphs. So they had to do something different, but it kind of similar ideas. And then finally, also some model theoretic simplifications of the proof. Or I don't know, I don't want to make a big point on this, just sort of clarifications on the proof, simplification following some recent work with Pillay and Pillay student Nicolas Chavarria about continuous logic. So okay, so it's like a different setting also about stability, but somehow looking at this perspective helped clarify there's different ways of looking at stuff. Okay. So now let me state precisely the theorem that we aim to prove. And I maybe since people have already asked, I should yeah, that's fine. I'll use this board. So we're now going to move to bipartite graphs. Bipartite graphs. So a bipartite graph will look like two vertex sets, which you would think of as being disjoint, but model theoretically they're like different sorts or something. VW, and then an edge set E, and here E is just a subset of V cross W. That's it. And so maybe it's okay if I don't, you can ask me to clarify if you want me to, but so K stable, this just transfers analogously. So what do I mean by a K stable bipartite graph? I mean the same thing, except now my edges are going between these two sets. So hopefully that's okay. And then also, if I have some subset X and V, and then Y and W, I can compute density, right? Same definition. And then now here, you don't have to worry about the ordered, unordered thing. So that helps a little bit. And it's just the same computation. Yeah, so I'll be saying some remarks. Yes, I'm going to be saying some remarks. There's something worth saying there, and I will be saying it. Yeah, okay. I'm just writing this here so everybody's comfortable now. I'm just going to switch to bipartite graphs without saying more. So if you want me to clarify a definition or something, that's good. But I will have some remarks after I state the theorem about, how to actually reconcile the two things. Okay, so I'm going to call this theorem A. So now I'll state, yeah, and it's basically the statement of Mallier-Sherlock more precisely with some, in the bipartite setting, with some extra tweaks. So it says, for all integers k greater than or equal to 1, epsilon greater than 0, and function. So I'll explain the role of this function as we write the statement. So I'm going to call it sigma from the natural numbers to the interval 0, 1. So I'll be explaining what's the deal with this in a second. There exists some number n depending on these fixed objects. So depending on k, epsilon, and sigma, such that the following holds. Okay, so now suppose I have V, W, E, which is a k stable. So k is fixed, bipartite graph. I'll write the word bipartite here once for emphasis, but that's just a setting. Okay, and then I should say finite. K stable, bipartite, finite. Where does it go? Here? Isn't there some like Oscar Wilde quip about ordering adjectives? Okay, doesn't matter. Yeah, finite. Okay, so then that just means V and W are both finite sets. Then there exists partitions of both pieces. So I partition V into V0 union V1 union Vm, and W I partition into W0 union W1, possibly some other number n, because these could be like very unbalanced bipartite graphs, for example. But the number of pieces in the partition is bounded by our capital N. So with, let's just do it over here. So with m and n, little m and little n at most big N, such that, okay. So 1, and kind of matching to Zemureti's regularity lemma now, but in the bipartite case. So both V0 and W0 are error sets. So V0 is at most the size epsilon times the size of V, and same thing with W. So size of W0 is at most epsilon times the size of W. So these are the like exceptional vertices that we're ignoring. 2, the rest of the pieces are the same size. So Vi equals Vj in size, and Wi equals Wj in size for all ij at least 1, and at most either m or n, depending on which you're looking at. And then finally, the third condition. Okay, so yeah, so far going back to the general regularity lemma, this is like 1, but in the bipartite case. And then 2, we're just going to say more briefly, and then Caroline already kind of pointed this out, but the point is that for all ij in m cross n, so maybe I should just say this is notation for the set of integers 1 to m. And similarly for other. Okay. So for all of the, after you ignore the exceptional vertices, for all of the other pairs, we have this 0, 1 density property, which then will imply regularity. I'll write that down carefully in a second. So if I look at the density between Vi and Wj, it's very small. And now finally, here's where this function comes in. not only is it maybe like bounded by this fixed constant epsilon, it's actually size at most sigma of, and really it's just sort of any function that involves both m and n. So I'm just going to put m times n. There's nothing very special about multiplication here, so don't like worry too much about it. It's just to denote that it involves both m and n, or the other way around. The density vi wj is at least 1 minus epsilon times sigma mn. Okay, so I want to say some words about this. There's several remarks to make about how to compare this theorem to the others, but still interrupt me if you have like questions about what anything means. Okay. Okay, so the point here with this function sigma is, yeah.
It's a bit weird that it's not completely symmetric one, which would be epsilon times sigma and then that one.
I'm sorry, this is just a, thank you. Just one, yeah, that was just a, short circuiting. 1 minus sigma n, yeah. So epsilon in the 0, 1 density statement, epsilon gets replaced by this possibly even smaller number that's getting smaller with m and n. And then that's the density that you have. Okay, so I'm just going to say some things out loud about this because it's important, but then also, I don't know. So then it's probably not going to tell you very much. Yeah, you want it to be, you want it to be, so like to, right, so, okay, so number one, okay, let's make some remarks. Let's just go ahead and make some remarks and I'll say some things as we go along because this will be good. Yeah, okay, so I want to make some remarks as I talk about this stuff. I think, okay, the one thing I wasn't going to write down is that by putting, I'll say this at the end, sorry. Okay, does this move? Yes. So the first thing I want to say though is that if you want to look at this recent work of Terry and Wolf, they prove this using finite methods. So you can prove this with quantitative bounds. So quantitative proof, not a model theoretic proof, quantitative. I don't know if that's probably not right. Quantitative proof. In this recent work, but it's in some sense you have to look for it in their paper because their work was really about hypergraphs, not about graphs, but they use this kind of stuff about graphs along the way. So it's not like the main result of their paper. It's like a tool in there. Okay, now two, how can we start reconciling the things? So first thing, as the Tai was saying, right, the theorem is about, the Maillard-Shalat theorem is about graphs. This theorem is about bipartite graphs. Well, given a graph VE, I can apply this theorem to just the natural bipartite graph I get from the graph. So I'm just going to write it like this. So I think of like two disjoint copies of V, and then the edge set is already a subset of V cross V. It's like a symmetric subset, but fine. And then, and apply it with just the constant function. Sigma is always equal to epsilon. That's a perfectly fine function to use. And then you'll get essentially the Maillard-Shalat result, but without the bounds. Okay, we've already ignored that. The one other little tweak, which I think, at least in the model theory literature, people sometimes forget to talk about, is that it's not a priori from the statement of this theorem, you might get different partitions, right? Like V and W get treated differently. Those could possibly be different partitions. But if you're worried about that, it's clear from the proof. I'll try to remember to say something about this. Clear from proof that, hopefully everybody will forgive me for just writing this informally, the partitions are the same. Actually, I'll write it. M equals N and Vi equals Wi for all I. So you'd have to do some work. There are other ways to get around it if you change the epsilon. In fact, it's even a bit easier since you have this function. You could just pick a different function that grows even faster and take care of it that way. But I think the most natural way to see this is when we go to the proof. It's going to be clear that if you're looking at graphs, we're going to be working with the same Kiesler measure, just to give it away. So the proof, clear from, does it say clear from the proof? It's not clear now because I haven't given the proof, but it will be.
And Gabe, you mean VI equal WI, right? Not WJ.
Yeah, thank you. Yeah.
So, like in my proof, if you apply the sigma equals epsilon, you won't be able to recover that without using basically one.
Yeah, I'm going to say something about that. Yeah, that's actually the most complicated thing I have to say probably before the break. Okay. Yeah, so today's kind of, like I said, mostly setting up the combinatorial framework, a little bit of, and then a little bit of model theory, and then all the main model theory will be mostly next week. Okay, so then now one small comment I want to make, just to, Caroline already said this, but right, I've stated this to say that you have this small or large density, but I haven't stated that that actually gives you regularity as stated in Zemmoretti's regularity lemma. So I just want to make a remark. It's very straightforward exercise, just counting edges and stuff. That if you have a bipartite graph, VWE finite, and you have subsets X contained in V, Y contained in W, if you know you have this 0, 1 density behavior, so if say delta XY is less than or equal to epsilon, or delta XY, the density is at least 1 minus epsilon, then it's a fairly straightforward computation to see that the pair XY, yeah, is, I mean, okay, sorry, maybe I should, maybe just psychologically I should call these like VI and WJ, because it's not the same X and Y in the definition of regular. Well, it's a subset of V. Okay, yeah, I'm going to change it to this, VI, WJ. It doesn't, all of it would have been correct. But just to match what's written over there, if you have this, that this density between VI, WJ is close to 0 or close to 1, then as defined over there, in VI, WJ is like cube root of epsilon regular. So you have to shift, you have to change the epsilon a little bit, but that doesn't matter. So if we give a statement that involves this 0, 1 density, then you get the regularity for free, which is why you can like forget about this definition now, because we're only talking about, and then some people call this homogeneity when you have the 0, 1 density property. It's like a strong form of regularity. Homogeneity is a buzzword that's often used. Okay. I want to leave that for a while, so I'm going to leave it. Okay. Any questions? Okay. So in fact, I'm going to go ahead and just erase the regularity lemma now, the general one. Oh yeah, the last thing I wanted to say that I wasn't going to write about the function sigma, actually, yeah, is okay. It makes it for a stronger statement because you can now pick. So I use this word decay function or control function sometimes, but that's not standard. But you can kind of fix. You can have this functional control on this homogeneity condition. This is kind of more relevant, especially in the setting of so-called analytic regularity limit that has to do with functions. It's also extremely important in hypergraph regularity in the Terry Wolf work. But it makes certain things easier. In particular, it makes the following thing easier, which I'm going to actually say a little bit about now, which is kind of nice. So this is remark number 4, which actually is going to have a little more content. Suppose we have theorem A, but I don't prove 2. Suppose we have theorem A, but we don't necessarily know that the non-exceptional pieces have the same size. Then I'm going to claim that by just changing the function sigma a little bit, it's actually very easy to get to an equipartition. And it will be clear from how you do it that if you started with the same partition before, you would get the same partition again, just to answer your question. Okay. So, well, okay, I'll say it again when okay. So then I claim that theorem A follows, and I'm just going to sketch this. Okay. Okay, so by change, if we have a version of theorem A where I don't say 2, and I just say I have some pieces, vi, wj of whatever size, if I have that, then I can do a short argument to get the pieces to have the same size. And this is also this is nice because there's like, this is also something that doesn't appear so much in the model theoretic literature either. You'll often see people do the model theoretic proofs and just leave it not being an equipartition. And yeah, there's various ways of turning a partition into an equipartition. If you allow yourself to have irregular pairs, it's much easier because you just keep throwing things into the irregular pairs. But if you want to have stable regularity with no irregular pairs, it's actually a bit harder. And so this is one nice reason to have this function. It makes it very easy. So let me just sketch that. So idea, it's mostly just a computation, so I'm not going to go through all the details. Idea, so fix, so again, suppose we have theorem A without 2. I want to prove theorem A with 2. So that means I need to fix a k, an epsilon, and a sigma that we want to prove the theorem A for. So fix k, epsilon, and sigma without loss of generality, just to make everything nice. I can assume this is decreasing function. So as my input gets bigger, my approximation is getting better. Okay. Right. Okay. Now I'm just going to draw a picture. I'm going to tell you what to do, and then if you want to check the sums and stuff on your own, it will all work. So I have V. I'm going to try to make my picture nice. So I have. So now, right. Okay. So fix k stable finite EW E. I know I can get a nice partition like this without 2, and then I want to turn it into a nice. I want to refine it into a partition that is that it does have this equitable thing. Okay, so here's V. I'm going to try to make this picture somewhat okay. Here's W. These are my vertex sets. Right? And so what I'm going to do is apply what I know, apply theorem A without 2, but using different parameters. So, okay, the k will be the same. I can't change the stability of the graph. It's still a k-stable graph, but I can change epsilon. I could apply it with epsilon over 2, and I can change my function. This is the most important part. I'm going to apply it with the function sigma prime of n. I'm just going to tell you a function that works, but I'm going to leave out all the computations you can check on your own. So this function won't, it is a function that works, but it's epsilon squared over 4n times the old function sigma applied to 4n. And then I essentially want to say epsilon to the -2, but okay, I made it an integer, so it doesn't matter. I shouldn't have even done this, but epsilon to the -1 raised up to the integer and squared. Okay, so this is a perfectly new function that I can apply theorem A without 2. I can apply it to that function. Is it okay? 2, yeah, exactly. And so then I apply it to here, and that gives me some partition, but it's not the one we want. So I get some like V0 prime, some W0 prime, and these are my exceptional vertices, the ones I ignore. And then it partitions the rest, but perhaps unevenly, right? So I get, here, 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 just trying to make a, okay. So this is like V1 prime up to some, and the number will be different. So M prime, whatever. So right, and when I apply theorem A, I get some bound. I'm going to call it N prime, depending on those different parameters. So I know that N prime is in most this. And then same thing down here. Some W1 prime, Wn prime prime, some other number, and again, this little n. Okay. Okay, and then all I need to do now is very simply just go into each of these pieces and cut them up into even sizes the right way and throw away the leftovers if I run into trouble. So I'm just going to show you on one of them. Well, I was going to use some colors. So I go into, say, I'm going to do this with each piece. I'll do it on a big one so it's easier to see. I go in and I just start cutting these up into pieces of even size. And I might run out. And so this is going to get thrown into the exceptional set also. So I'll shade it like this, the new exceptional set, because we're changing everything. And what size do I pick? Here's something that works. I'm going to want all of these, each of these little pieces in here to have size exactly ceiling of epsilon over 2m prime times the whole size of the vertex set. Okay, and then since everything's an integer, when I run out, I will know that this part over here is at most epsilon over 2m times the size of the vertex set. That's all. That's at most what could be left over once I get out of trouble. So now inside here, these like red pieces, these each have exactly the same size, and this is something left over that I'm just going to add to the exceptional set. And then I do the same thing to the other side. So I go in here, cut it up. You know, maybe this is closer, but whatever. And then these are going to have size exactly, ceiling epsilon over 2n prime times the size of w. And then the leftovers will be at most epsilon over 2n prime times the size of w. Okay. And now I get a new partition of V. Oops. So I'm going to get a new V0, which will comprise of the old V0 prime plus whatever is left over, possibly in each piece, throw it all in there. And then what are the new V1 up through V new M? It's just all the rest of the sets, and there are going to be some number of them. We'll say how much. So is that clear what I mean? So I take away in each piece the stuff that I couldn't get a new piece out of. I throw it all into V0. And then the rest is just the rest of equally sized sets now. And then do the same thing on W. Some number N. Well, this colored shock is more brittle. And then, okay, if you just, I want to kind of make sure I have time to get to some of the model theory today. So, you know, I'm leaving out all the computations. But if you just do a simple counting kind of thing, I promise you this is not requiring any special combinatorial techniques, just basic computations. You can check that M is at most 2 times M prime squared epsilon to the -1. If you just bound how many possible ways could you cut these pieces up into even sizes, you get some loose bound. N is at most 2 times N prime squared epsilon to the -1. Doesn't matter. Both of these are bounded by 2n prime, capital N prime squared epsilon to the -1. Okay, and then that's our new bound. That's N. Okay. And then the thing I'm going to leave out entirely, because if you really care, it's much more informative to just check it yourself. But the thing I'm going to leave out entirely is that if you take an ij greater than or equal to 1, or sorry, maybe I should say so, given ij in M cross N. So take a VI and a WJ from my new partition. You'll have to check this if you want to, but you will have this. It's similar, yeah, but it's a little bit more counting, but it's similar ideas. But you will have this coming from the fact that the VI and the WJ came from sets that had a 0, 1 density with an even better sigma prime function that is tailored perfectly so that this will pop out at the end. And it's just, you know, if you really care enough, it's better to just check it yourself, and maybe you can pick an even better function. No, it's not. This is a non-trivial. I mean, it's a straightforward thing once you've got it set up with this function, but it's a non-trivial thing to do.
No, not saying the whole thing for it, but that's it. Because you know now it's regular, so it's like in the subset.
Oh, maybe you're right. Yeah, I don't know.
No, I mean, that's different. Because the VI and WJ there, they're the same set, right?
Yeah.
So I think what Atai is saying is that we know that VI prime.
think that's.
So I think what Atai is saying, and I would have to check this, but okay, we know that this is like some epsilon prime regular. So I could apply the regularity condition to the VI and the WJ, which are like some non-trivial, see what you get. Yeah, you might get it. Okay, so check it that way too. Maybe it makes it easier. I think it's probably not going to be as perfect as this because of that cube root. I think you'll lose a bit more going that way. But at either rate, yeah, you'll see that there's a way of just picking your new function sigma prime appropriately to get this to work. So that's really the point. The point is not like what exactly the function is. The point is that by changing the function, you can get something much more easily, just in one step like this, in a very naive way, just cutting it up into pieces and it works. So that's like all I'm going to say about that, I think. Okay, except for going back to the second remark, hopefully it's clear that if you knew your unbalanced partitions of V and W were like the same, then you would be doing the same numbers and the M and the N were the same. You would be getting this. You could do it to get the same balanced partition as well. But, all right. Okay, so maybe it's time for like a 5-minute break. And yeah.
Did this equipartition play an important role in the application to the similarity theorem? Equipartition play a role in this?
So I'll just say, yeah. Okay.
And the thing is, like, in the original, like when you.
So I just want to leave that board. Yeah.
So the actual regularity on the.
And also, I mean, and Caroline could correct me if I'm wrong on this, but I think when you're talking about regularity with allowing for some irregular pairs in general, the move between partitions and equipartitions is kind of more standardized or something.
And this, I mean, this strong function here is like more important for say like the like if you want it for induce.
Oh.
Like if you want to induce for the whole.
Okay. And I go till 12:30, right? Ish. 12:30, 1:30, 2:30, something like that. It's a joke. Let's have a little break now, 5-minute break. I said 5 minutes, right? So we use 2 minutes, yeah, but if you want another 2, it's okay. I said combinatorial improvements due to Terry. That's one of the improvements. No, yeah, I already explained. He's going to leave theorem A. I mean, Dr. Terry. Yeah. PhD. No, I don't mean. I'm not on a first name basis with either of them, in fact. Professor Peter. Sure. Should I blow on it?
Hey, it was okay this morning. It was alive. I don't know. I mean, he woke up pretty early, but he said he'll be in later. I mean, I don't know what. Yeah, but I hope he's awake. for a vote, paid vote. Sorry?
Seems like a guy who left. So is Hanukkah something that's celebrated in your household, or is the whole present thing seen as an American abomination? Bastardization of the whole.
It is, yeah, we do celebrate it and we do big presents as well.
I'm somehow given the impression that American culture has taken.
No, I mean, I think giving presents in Hanukkah is
Nice.
only the implementation. But I don't know, I think like everything, I mean, presents in holidays.
We have one more minute. Is everybody back? Shall I start again? Okay. Welcome back, everybody. All right. So part 2. So the goal now, part 2, I'm going to hopefully finish it today. In the remaining time, what I'd like to do is state the model theoretic results that we need and sketch the proof of the theorem A from the model theoretic result. And then next time we'll say more about the model theoretic context, clarify definitions and stuff, and prove the model theoretic result. That's the plan. Okay. So now we're going to go to a general model theoretic setting. So let M be an L structure, arbitrary. You could work in the context of a theory too, although here it's not so important. Also because everything I'm going to say works for the stability in a model setting also, although it's not needed for this. So now let's fix an L formula, say phi xy. Now I think I'm trying to make sure I follow Anand's terminology and notation stuff, but x and y now are possibly tuples of variables, if you like. Okay. So the one new definition, which I'm just going to state the definition, and then because of time, I'll say more about it next time, because I don't think this has come up in the course before, is the definition of a Kiesler measure. Okay, so a Kiesler, I'm going to use phi measure. The terminology here is not standard. Some people say phi Kiesler measure, some people say Kiesler phi measure, some people say something entirely different. But a Kiesler phi measure is a finitely additive probability measure on the Boolean algebra of definable, phi definable subsets, if I can use this notation, of the appropriate thing, m to the x space or whatever. Okay, so Anand defined phi formulas, phi definable sets. These are just, I take instances of my formula by plugging in parameters, and I look at the set I define by those instances, and then this is just the Boolean algebra generated by that, phi formulas. Okay, so this is a Boolean algebra, and so you can talk about a finitely additive measure on a Boolean algebra. So it's just an assignment of all the things in your Boolean algebra to some measure between 0 and 1. The measure of the whole thing, m to the x, which is phi definable, is measure 1. The measure of the empty set is 0, and then you have finite additivity. So I'm going to say a little bit more about this next time model theoretically, but if you want to think of an example, you could think of a type. So a phi type, I'm going to erase this. So we know what phi types are. This is a special case of a measure because it's a literally like 0, 1 valued measure. A formula has measure 1 if it's in the type. It has measure 0 if it's not at the type. Okay, so this I'm going to say more next time. But maybe to motivate for now, I mean, it's very natural that we would need to be talking about some kind of object like this because this theorem is about, the counting measure of sets, right? So, okay, how are we going to model theoretically prove a theorem that talks about measuring things without some notion of measure? Okay, so is that okay for now, just in terms of the definition? I guess maybe also for people online. I think everybody in the room is probably pretty comfortable, but okay. So I will say more later. What I want to do is just state the theorem. So this is called theorem B. So now assume that our formula is stable. And okay, you can take this to mean with respect to the theory of M, or you could take it to mean stable in the model as well, if you want. I think everything I say works in that case as well. What? Yeah, I will, because we're gonna, okay, I mean, it's not worth saying too much about this, but we're gonna apply the theorem to a saturated model anyway, so it's not a huge deal. Okay. And now let's suppose I have some Kiesler measures. So let mu be a Kiesler phi measure. And nu, another measure, so a Kiesler phi star measure. So maybe I should remind, I'll just put it over here. Sorry about the disorganization, but remember, phi star yx is the same formula phi xy, but you're just changing the role of the object variables and the parameter variables. Okay. So I have a measure on both sides, measuring phi definable subsets of m to the x and phi star definable subsets of m to the y. Okay, then for any epsilon greater than 0, there exists some integers m and n. I'm just going to write this greater than or equal to 1. So there's some alternating quantifiers here, so to deal with it, such that for any other number gamma greater than 0, and this is going to look weird, but the important thing is the gamma comes after the m and n, and this is going to be reflected in being able to pick this function. Okay. All right. For all gamma greater than 0, there exists partitions. So a partition m to the x, v0 union v1 union vm, and m to the y, w0 union w1 up to wm, satisfying some properties. Okay. So first, each vi is a phi definable set, so it's something I can measure. And each wj, and here I really mean all of them, including the exceptional one, although of course each wj is phi star definable. The v0 and the w0 act like exceptional sets. It means it's in the Boolean algebra generated by sets defined by instances of phi, where x is the variable and y is the parameter. Just like a setup from Anand's course, when I partition it this way, the second thing is going to get the parameter. The first variable is going to be the thing that gets the space where I define something, and so the phi star switches it. Okay. 2, for second bullet, the measure of v0 with respect to mu is less than epsilon, and the measure of w0 with respect to nu is less than epsilon. So these are our exceptional sets. And then the third thing, I'm going to try to fit it here. So I'll just write it. Okay, so yeah. It's going to be a thing that is going to eventually give us 0, 1 density, but I'm going to write it out kind of in a more deconstructed way to avoid talking about, say, like product measures or something like that, right? Because when I talk about the density of a pair, that's naturally a density of some product set. And I don't want to talk about product measures. I think you can if you like, but I'm going to write something deconstructed. So for every ij in m times n, there exists some, think of it like a truth value, tij in 0, 1, and some phi star definable subset w prime of wj. So I'm going to write it out and then we'll say what happens, such that this W prime subset is almost all of Wj. So the new measure of W prime is at least 1 minus, but now gamma. So we're using our sharper parameter gamma that came after M and N. So times nu of Wj. So this is just saying W prime is very big. I throw away a little bit of Wj. And what I get is that if I take any point B in this set W prime, that's almost all of Wj, and then I look over here at the mu measure of the subset of Vi. I'm going to change things. So I'm going to look at what do I find by this, defined by this instance of phi inside of Vi, except I might take phi or its negation, and that's this, but it's uniform. It's this the same 0, 1. So if I continue here, so phi 0 means not phi, phi 1 means phi. So I'm going to look at either yes, there. Think of it graphs, right? I'm going to say yes, look at all the edges, or look at all the non-edges. This set, and this is a measurable set. It's an instance of phi or a negation. This is going to be at least 1 minus gamma times the measure of Vi. So it's something to parse. It's not as slick of a statement as 0, 1 density, which feels more meaningful, but it's saying that for every pair ij, there exists a uniform truth value, so that for almost all B on the right-hand side, for almost all things on the left side, they're either like all connected or not connected, depending on this uniform value Tij. Sorry, yeah. Bi. Maybe I'll draw a picture. So I have Vi Wj. I cut out down to this slightly smaller set W prime. And no matter what point I take in here, I have one answer depending on Tij. If Tij is 0, then almost none of the points are related to B by the formula. And if Tij is 1, then almost all of them. But it's the same 0 or 1 for every point I pick in here. Yeah.
And this reason for the asymmetry between W and V is because you first realize on the right and then you realize on the left.
Yeah, you could think of it that way. I could add a symmetric statement. I could say moreover. You can do it the other side, and moreover, the Tij would be the same. And this would either follow from the proof and symmetry of forking later on, or it actually also just, and okay, yeah. Or in the downstairs application, when we translate this to actually looking at edges of finite graphs, it would also just follow up to changing the epsilon again. So the asymmetry is like a red herring here for a number of reasons. Up in the model theoretic result, actually, maybe that's not true. In the model theoretic result, the fact that I can get a symmetric statement is non-trivial. I would need either some kind of Fubini condition on my measures, which I have, or a symmetry of forking condition, which is sort of the same thing, which I have. But I'm going to ignore these subtleties, I think, which is so yeah. So Yatir was just pointing out that there's asymmetry in this statement, right? I've picked W prime and gone over to V. You could write another statement and add that, and it would be essentially equivalent. But to save time, I want to just work from this. Yeah, but it's a good point. Okay. So that's theorem B. That's what we're going to prove next time. Just like that, as stated. And so what I want to sketch now in the rest of the time today is just how to get from theorem B to theorem A without the second property, because we've already seen how once I have it without the second property, I have it with the second property by changing the sigma. So yeah, so the goal for the rest of today is to sketch theorem B implies what I'm going to call theorem A star. All that means is without 2. So I'm ignoring the even size thing. Sorry about all the lines here. I mean, now I'm going to prove it. And yeah, I hope I have actual time to get through it, because if I had to stop in the middle, it's going to be a bit weird. But and I was kind of, I don't know, I was contemplating whether to actually even do this part. This is the ultra product part. So I think I'm going to do it, but unfortunately, I'm not going to have time to like give an introduction to ultra filters and ultra products. So anybody, if you're not familiar with that, you'll just have to kind of absorb the whatever. Okay. Sorry. Okay, so let's assume theorem B. So, all right. Although it's worth saying, I think pedagogically, right, this is a situation where I have a theorem about finite structures and I'm going to prove it, an asymptotic theorem about finite structures, and I'm going to prove it using one theorem about a single infinite structure. So this comes up a lot, and the ultra product method is standard where you do this kind of process, and the way it goes is that if you have your asymptotic statement about finite structures, you assume it fails. It gives you a bunch of counterexamples showing that you can never get your bound, and you take an ultra product of those counterexamples and apply your upstairs theorem to that, and then derive a contradiction somehow. Okay, so we can end early, right? Just kidding. All right. So suppose theorem A fails. Theorem A star, I should say. Okay, so what does that mean? It means that we have a fixed K, epsilon, and sigma. So I'm going to try to run through this kind of steadily so that we get to the end. So we have a fixed epsilon, K, and function sigma from the naturals to 0, 1, such that, and I'm going to change the letters here, I apologize, but basically, what does it mean for this to fail? It means for any integer I pick, it doesn't work. No capital N works, but I'm going to switch to the letter lowercase s, just to, okay. Such that if I pick any s greater than or equal to 1, then there exists a counterexample showing that that bound will not work for capital N. This number s will not work. And what does that mean? It means there exists a k-stable bipartite graph. So VSW at some vertex set, some vertex sets, some edge set, finite, such that, and I'm not going to write it all out. I'm just going to say the conclusion of theorem A star fails for all little m and little n at most s. So I cannot take this k-stable bipartite graph and partition it up satisfying 1 and 2 so that the numbers little m and little n are bounded by s. Okay? All right. Good. So now we're going to view these as model theoretic structures and take their ultra product. So view, and this is where I'm going to start to be a little bit informal maybe. But view this as like I'm going to say a two-sorted structure. You could use unary predicates for the v and the w if you want to as well. You just have to write more things down. So, okay, you view this as a two-sorted structure. In the natural language, a sort for v, a sort for w, and then the binary edge relation going between the two. And then, okay, we need to talk about the measure, right? We need to actually talk about transferring properties about the measure. And there's various ways of doing that. I'm going to do it in the following way. Add a third sort for the interval 0, 1 with like the order relation, maybe. I don't think you need addition, but why not? Truncated addition, order, I think that's enough. I think order by itself is enough, probably. Okay. All right. And then for any formula psi of xy bar, which is a Boolean combination of instances of the edge relation with x fixed and then some yi, so that's where I get my tuple here. For any formula like that, I'm going to add a function symbol that's going to measure the size of the subset of the x space defined by instances of this. So let me write that down. Add a function symbol. I'll call it f psi of y bar. So it's going to go from the natural sort to the 0, 1 sort. What does it do? How do I interpret it? In each structure, I interpret it as sending a tuple b to the size of, so if I'm in the S structure, it's the size of the set defined by this instance, and I'm going to normalize it because Kiesler measures are probability measures. So I'm not actually using the counting measure. I'm using the normalized counting measure. Okay. Is that okay? Okay, and then we do the same thing for the other side. So similarly, expand for Boolean combinations of instances of the edge relation where I fix y and allow the xi variables to be different. Okay. Okay. So that's how I'm going to look at for each s. That's how I'm going to look at this finite structure, but it has this extra sort for 0, 1, and okay. So this allows me to then just put those counting measures into the language. Now, okay, now let U be a non-principal ultra filter on the natural numbers, and we'll take the ultra product. And I'm going to suppress the 0, 1 sort from the notation. It's there. I'm going to take an ultra product of that. Okay. So I'm going to let M be, so it's going to have some VWE. It'll be the ultra product of these, along with the other, the 0, 1 part, right? So I'll get this ultra product of the interval 0, 1, 2. All right. Okay, and now here's the part where the order of the parameters is really important, right? For all s, there's this fixed k. Each s is k stable. The k is not changing. So each one of these finite structures satisfies a formula saying this graph is k stable. So by Wash's theorem, that transfers to the ultra product. So by Wash, EXY is k stable in M. So this is why it doesn't, for us, it doesn't really matter this in a model thing because it's going to be actually k stable. Okay. And now, okay. So I'm gonna. It's sort of dumb to do this because this is already a formula, but I'm gonna let phi xy be this formula just so the notation matches. So that's the formula I'm going to be applying this to sort of clearly. Okay. So now recall, if I look at my structure M and I look at a definable subset, say, of V, any definable anywhere, it doesn't have to be phi definable, although that's all we're interested in. Any definable subset, say, X of V, can be written of, is like an internal set in the language of ultra products. So is of the form ultra product over U of Sx for some subsets, some finite subsets of the structures. And so this gives me a way to measure them, to measure definable sets. So I'll let mu of x equal the ultra limit of the normalized counting measures of these components. So this is a well-defined limit that does not depend on how you represent your definable set as an ultra product. These are all sort of standard parts of the machinery here. So this gives me a well-defined number in 0, 1. Okay, and so the fact easy thing to check is that if I look at what mu does, say, just on the phi definable sets, that's all I care about. So mu, I'll just write this, mu determines a Kiesler phi measure. Period.
We're not using this for any definable.
Yes, but I've only defined measures on the phi formulas, so I don't want to. It is a Kiesler measure on all definable sets, but I didn't define that.
What's the reason for this F sub C on that one?
Yeah, so the reason, moreover, if I look at, so I'm not going to rewrite, but if I go up to here and look at this psi, which is like a phi formula, right? If I look at the measure of some instance of a formula like this, so some psi xb, which is a Boolean combination, it is precisely the standard part of whatever this function symbol now interpreted in the big structure does to these parameters in the big structure. So the point is that now I can write down sentences and axioms that talk about measures of formulas using, up to some, inconsequential loss in the standard part. I can talk about measures of sets using these function symbols. So this is one place where working in continuous logic kind of makes things a lot easier. You don't have to do all of this, but okay. Okay. Good, I think we're gonna, all right. Yeah, sorry. Okay, so then similarly, do this on the other side. Similarly, obtain a Kiesler phi star measure nu. Okay, so maybe Anand's point was that you could define the measure mu directly as the standard part of the function here and not actually take an ultra limit. So yeah, you could do that also to define the measure, but I think this is sort of a very natural construction, so which doesn't depend so much on the syntax. All right. Okay, so now we've got our stable formula phi xy. We've got our two measures, mu and nu on both sides, and so we apply theorem B. So apply theorem B with. So theorem B says for all epsilon, so I can apply it with our fixed epsilon. And then theorem B gives me some m and n, depending only on epsilon. So for all epsilon, there exists an m and n. And then but this m and m holds some for all gamma, so I'm gonna apply the conclusion of B to a particular gamma, which is now going to be the function sigma mn and divided by 2 for a particular reason having to do with the precise difference between a statement like this and the actual 0, 1 density. I'll say this at the end. Okay. Okay. So that's why this new alternating quantifier thing is important. The gamma comes after the mn, so I can pick it using this function. Okay, now yeah, I am going to just kind of state what you do now, and if you can check it. But propositions, so proposition main exercise. I have this statement that says that I can partition m to the x and m to the y into these definable sets having these nice properties. And what the proposition is going to say is that you can write all this up as a first order statement and transfer it to, have it hold for mu many things. So there exists some set I in the ultra filter such that for any index s and I, there exists partitions of vs into, okay, so I have to do my numbers now. So vs sub 0 union vs1 union vs m with we've gotten m and n. And ws is partitioned into ws0 union ws1 union ws(n) such that it's just the natural translation of those three bullets. Okay, actually the second two bullets. I'm going to ignore the definability. I mean, you can say more. You can say that these sets are like given by instances of the edge relation, but it's a nice thing to say, but I'm not going to write it out explicitly. I'm just going to translate the second two bullets to the finite setting. So to say that the normalized Kiesler measure of the Vs or the V0 is small translates to saying that Vs0 is at most epsilon times the size of Vs, right? Because I would divide by Vs to get the normalized thing. And Ws0 is at most epsilon times the size of Ws. And then just rewrite the second bullet. Oh, that's not going to work, is it? Maybe it's okay if I cover part of it for a second. For all ij, other than the exceptional sets, there exists a uniform truth value Tij in 0, 1, and there exists some set W prime. I mean, we're not quantifying over subsets because this is given by a formula upstairs. And so I use that same formula in the transfer. So you do have to write this out carefully, but you can believe me that I do it. So inside of WSJ, such that its measure is big. Yeah. W prime is at least 1 minus gamma times the size of WSJ. And so for almost all things in the WSJ, if I take somebody B and W prime and I look at its edge neighborhood or non-neighborhood according to my truth value. ESI, comma B. I look at what is the edge neighborhood with B inside of the ith thing in the partition, or maybe the non-neighborhood, depending on this thing. It's at least 1 minus gamma times the size. So let me come back to that. Good. Yes, great. Good. Now you'll notice I put strict inequalities here and weak inequalities there. And that's just for so that you can account for the standard part map. You can just pick something small and get it to work. So it's actually important, but it's not, whatever. All right, let me move this up. Okay, so then the last thing I'll say today, right? So theorem A, what do we have? Okay, yes. No, we haven't finished the proof. What am I talking about? Where should we go? Here. Okay. So now here, another easy counting exercise. This implies that, for all S in this proposition, and for all I, J, whatever, if I compute the density between VSI and WSJ for IJ other than the exceptional vertices, I'm going to get at most 2 gamma or at least 1 minus 2 gamma. And recall 2 gamma equals sigma. Thanks. Okay. So if you take this bullet, it's just easy to check that second bullet here implies this. It's not hard. Okay, and so now I get a contradiction to assuming that these were counterexamples to this theorem, because for S and I, I've got this for that particular one, and I've got this for that particular one. And so I get a contradiction as long as S is bigger than M and N. But now here's where I use the fact that the ultrafilter is non-principal. So pick S and I that's bigger than these fixed bounds, contradiction. Okay, so that's the end of the proof. I mean, I left out a lot of checking little details. A, sort of basic things about the structure of ultralimits, ultraproducts. And then 2, the very careful writing down of that this actually is a first order thing using our expanded language, but it's all bookkeeping there. So yeah, well, did I erase the exact part? I think I did. That was bad. If you see through this, I picked VS, WS, and ES, oops, to exactly not do this, to do exactly not this for any MN less than or equal to S. And M and N are fixed, so I can pick S big enough since the ultrafilter was non-principal. The set I is infinite. So, yeah. So yeah, I mean, all the theorems like this I think are a little bit kind of strange because you prove by contradiction. You suppose it doesn't work, and then it does work upstairs, but then it doesn't work. So it always makes you think you could rewrite it as a contrapositive, but I don't think you can. It's really this is how they look. So that's it. Any questions for today? So sorry, next time I'm going to prove theorem B and say a little bit more about the model theoretic context. No, I mean, I think if your measure was, if the mu and nu were actually types, this would be completely trivial because all the measures concentrated on one point. Okay, but you have to prove that. So.
Oh, but I mean, after that.
Yeah, I mean, that's the content of the proof, but that's spoiler alert next time. You know, so, yeah. No, I'm not. So this was part of this discussion that if you wanted to turn this into a symmetric, if you wanted to add a symmetric statement, you could, just period. And then if you do that, then your TIJs a priori could be different. But they're not either by symmetry of forking or by a Fubini thing, which is somewhat the same. But I'm not saying anything much about that.
In the thing that I wrote about Ariane, use explicitly forking symmetry.
Yeah.
But I'm not sure that was actually necessary.
It's not. If for proving, at least for proving the downstairs theorem, it's not, because look, from this one-sided condition, I get the 0, 1 density. And then it's easy to show that from the 0, 1 density, you can also get a condition like this, again, maybe changing the epsilon, but then, you know, this is clearly a symmetric condition, so you can get it on both sides. At the finite level, you can get both things going through the density calculation up to changing the epsilon. So this is why it's just not really a crucial thing if all you're worried about is proving the finite statement. But if you're interested in the general theory, and I think there will be time next time because the proof of theorem B is actually not that long, you can discuss that. You know, if you want a statement, because this is a statement of arbitrary structures, not just pseudo-finite structures, arbitrary measures. So it might be nice to know that you've got a Fubini type condition to get a symmetric statement here, and you do, but it's just not necessary for this application. Yeah, but the proof of theorem B.
So what is your
Right, okay, maybe that's a good thing to say now. So if you were actually taking the ultra product of graphs, then your phi xy would be, x and y would be from the same sort, and it would be a symmetric formula. So the mu and the nu would be equal. It would be the same counting measure, or the same pseudo-finite counting measure. So then when you look at the proof of theorem B, you'll see that you're decomposing the same measures, and so you get the VI and the WJ to be the same. Yeah.
Before the sense of statement B, it's just like a pure model theory statement. Right? It's just about simply the statement before.
Yeah.
Right? But then it turns out to be one of the connected to this.
Yeah. So what Anand said for the people is that this is a pure model theoretic statement. It's relevant to the combinatorics. Obviously, I've written it in a way that's very suggestive about measures, blah, blah, blah. It looks like a regularity statement, but we're going to see next week in the proof that the key thing is what Itai said, that I can write a measure as a sum of types. That by itself doesn't look like it has anything to do with regularity, but in some sense it is the thing. It's the thing. Okay, so yeah. Thanks everybody. See you next week. Oh, thank you. Don't have to wait till the end of it. Thanks, Christian. See you later. What's that? Oh yeah, so next week again is I'm sorry for this, but it's going to be at 9 a.m. to accommodate the workshop. So if you miss it, it'll be recorded, of course, but 9